Section 1.7b is about deductive reasoning and counterexamples. We're going to start by defining what deductive reasoning is. It's the process of using facts, rules, and definitions or properties to reach a valid conclusion. Detectives do this all the time. Sherlock Holmes does this. They use things that are available to them, facts and rules and to reach conclusions that they can then say are valid conclusions. And we're going to do stuff like that, starting with this first example down here. It says determine a valid conclusion that follows from this statement. If two numbers are odd, then their sum is even. Now, one thing before I go on is I'm going to highlight the hypothesis, two numbers are odd, and then I'm going to highlight the conclusion, their sum is even. Now, that's important, as you'll see in a minute. Continuing on, if a valid conclusion does not follow, then write no valid conclusion. So what we have to do is tell ourselves if there is a valid conclusion, but if there's not, we have to say why there's no valid conclusion. We'll go back to the statement. If two numbers are odd, then their sum is even. If you're going to have a valid conclusion, your hypothesis has to be true. It has to be. You can't have a conclusion without a true hypothesis. So the big thing we're looking for in both of these examples is the hypothesis true? Let's take a look. The two numbers are 7 and 3. We'll go back to our hypothesis. It says two numbers are odd. Are both these numbers odd? Yes, they are. Therefore, since the hypothesis is true, and I'll write that down, the hypothesis is true, because that's the fact, then we can say our conclusion is the sum of 7 and 3 must be even. And that's the conclusion that we have to have, because that's what our conclusion of our conditional statement is. Their sum is even. So first you have to see if the hypothesis is true, and if it is, you can write a valid conclusion. Our second example, it says the sum of two numbers is 14. Well, again, go back to the hypothesis. Is the hypothesis true? Two numbers are odd. Well, it doesn't give me two numbers. It just gives me their sum. The point is that our two numbers do not have to be odd for the sum to be a 14. So we would say here that there is no valid conclusion. And the reason we say that is because we can't show the hypothesis to be true. So if you can prove the hypothesis true, for sure, then you can have a conclusion. But if you can't prove the hypothesis true, if it's not necessarily true, you have to write no valid conclusion. Now we're going to talk about counterexamples. A counterexample is a specific case in which a statement is false. It's a way that you can look at a statement and you can prove that that statement is wrong simply by giving it an example. A specific example would be if the student said all teachers are nerds, and I gave the specific example Mr. Hardy. Because Mr. Hardy is not a nerd, that proves the statement that all teachers are nerds, that proves that statement is false. And that's an example of a counterexample. Let's look at some others. It says find the counterexample for each conditional statement. If you are using the internet, then you own a computer. So if you're using the internet, are you sure that you own a computer? Is that a true or false statement? Well, obviously it's false, but let's give some specific examples to why it's false. You could be at the library. You could be using your phone. You could be stealing Wi-Fi from a classroom or a friend. Okay, these are three actual counterexamples. We only need one. One example that proves that the statement is false shows the statement is false everywhere. So these are three counterexamples. Let's look at the next one. If the commutative property holds for multiplication, then it holds for division. Well, remember the commutative property says that 3 times 2 equals 2 times 3. That's the commutative property, which is true. 5 times 10 equals 10 times 5. That's the commutative property for multiplication. Well, according to this, if that's true, then it's got to work for division. Let's look at the second one here and show why it's not. 5 divided by 10, does that equal 10 divided by 5? Well, 5 divided by 10 is a half, or 0.5, and 10 divided by 5 is 2. So that's not true. So that's actually a counterexample which shows that this statement, that the commutative property holds for division, is false. These are examples of counterexamples, statements that are specific cases that prove statements false. Here's some more examples of deductive reasoning. we're going to look at the statement and then try to find a valid conclusion, and if no valid conclusion is there, we write that down. So our statement is if the last digit of a number is 2, so the hypothesis is last digit of a number is 2, then the conclusion, the number is divisible by 2. So that's the statement we're examining right now. Well, our first one says the number is 10,452. Remember, it's important to look at the hypothesis. Does this match the hypothesis? The last digit is 2. Yes, it does. So because the last digit is 2 and it matches the hypothesis, we can say that the number is divisible by 2. That's our conclusion. We get that because the hypothesis is true, therefore the conclusion is true. Second one, the number is divisible by 2. Well, we don't know about the hypothesis for that one. The last digit of the number is 2. What about 14? 14 is divisible by 2, but the last digit is not a 2. So the point is we can't prove the hypothesis is true in this specific case, so we say no valid conclusion. And then the last one, the number is 946. Once again, the last digit has to be a 2, and it's not. So we can't prove the hypothesis true. So again, we have to say that there's no valid conclusion. Even though we know that 946 is divisible by 2, we know that, but it does not match my hypothesis in this specific statement. So we must say that there's no valid conclusion based on our statement. Here's some more examples where we have to find counterexamples. Remember, a counterexample is a specific case that proves the sentence false. If Anna is in school, then she has a science class. Is that always true, or can we find a specific case? Well, what if Anna doesn't have science this year? That would be a specific case in which this statement is not true. Second one, if you can read 8 pages in 30 minutes, then you could read any book in a day. Now, you could figure out what 8 pages in 30 minutes is. That's 16 pages per hour, 24 hours in a day. You could figure out how many pages that is. But I can give you an example by just giving any book that a person that reads this fast could never read in a day. And my specific example will be the Bible. You can't read any book in a day because you're not going to read the Bible at that speed. You could say an encyclopedia or something else. That would be a counterexample to show the sentence is false. Next one, if a number x is squared, then x squared has to be greater than x. So I don't know, you can just try some stuff. 2 squared, that's a 4. Is that greater than 2? Yeah, that's true. So that appears like it will work. How about, I don't know, 5 squared is 25. Is 25 greater than 5? Yeah, that's true. It seems like this might be a valid conclusion. But remember, all we got to do is come up with one example. And I got one for you. If you square 1, what do you get? You get 1. And is 1 greater than 1? No, it's not. So actually, I should probably leave that because that is my counterexample. But I can put the little slash through there to show that it's not greater than. So there's my counterexample. X being a 1 is bad because it doesn't work. Next one, if 3x plus 7 is greater than or equal to 52, then x is greater than 15. Well, that appears to work. Anything bigger than 15 makes this true, except x equaling 15. See, if I put x equals 15 in here, I get a 45 plus 7 equals 52, and that works. So x equaling 15 is my counterexample. It's the one example that proves that statement to be false.